All right, section 4.5 is called the fundamental theorem of calculus. So anytime you see the fundamental theorem of it means that it's awfully important, right? And you've probably seen it at different points in math classes you've had before. Maybe you've seen something called the fundamental principle of counting, or you might have seen one in trig, but I don't remember what the name would have been. This is a very important section of material. So to start with, this is the fundamental theorem of calculus. It is part 1 of the theorem. We'll do part 2 in a little bit more. It just says that if we have a continuous function on the interval AB, capital F is the antiderivative. You've seen that notation before. Then if you take the definite integral from a to b of your function, it's the same thing as taking the antiderivative and evaluating it at the point B, and then subtracting the evaluation at the point A. This brings everything together from what we've been doing in this chapter. Okay, the last section in this chapter is going to go just a little bit further down this bunny trail, so to speak. But this really is the culmination of what we've done in this whole chapter so far. So let me show you how this works. We're going to take an example. Our example is the integral from 2 to 5 of negative 3x plus 4. And what we're going to do is we're going to take an antiderivative. So, antiderivative quiz, many of you still need to come see me. In fact, almost everybody. So, please don't let that slip off your radar. We need the antiderivative of negative 3x plus 4. What in the world is that antiderivative?
Minus 3x squared divided by 2
Okay.
plus 4x.
Okay, does everybody agree? I'm going to get to the plus c here in just a second. Does everybody agree so far? Okay, so and then on your quiz, we talked about putting plus c's on everything. I'm going to put the plus c on here for right now, and I'm going to work the problem out. And in the end, we're going to talk about the plus c one more time. Okay? Everybody good with it so far? All right, what you're going to do next is you're going to put a vertical line at the end. And you're going to take the values that were at the beginning over here, 5 and 2, and you're going to put them on the top and the bottom part of this vertical bar over here. So you're going to do 5 up here, 2 down here. So wherever the values are, they stay. You don't switch them, even if the bigger one's on bottom. You leave them where they are. Okay? And then what do? Well, this slide over here says what I need to do is I need to plug the value in to the antiderivative. Right? So over here, we're going to take the first one, negative 3. We're going to plug in 5. So 5 squared over 2 plus 4 times 5 plus c. We want all of that. And then we want to do the same thing at the value of 2, and then what? Subtract. Very good. All right, so then I'm going to put minus right here. I'm going to sort of write the subtraction in now, and I'm going to write the exact same thing, but with the 2 plugged in for x. So now as you're working the problem, you might be again asking, like probably you normally do, what in the world does she really want to see on my paper? I want to see the step that shows you know that you're plugging the value in. Now eventually, when most of you are on into Calc 2, for those of you who are going on, this sort of becomes a step that you don't really show that much because you've done it enough that we know that you know to put the numbers in. But that's actually what I'm wanting to make sure right now, is that you understand where the numbers go and so forth. Okay? Now at this point, well, now's as good as any time to talk about it. What's going to happen with those plus c's? They're going to cancel out, right? Why? Right. This is actually plus c. This plus c has the minus in front of it, so those two are going to cancel out. They're going to add to 0, right? So what does that mean for us? Well, it means that when we do definite integrals and use the fundamental theorem of calculus, we don't have to write that plus c here anymore. So how do you know when you write the plus c? Well, you write the plus c when you don't have numbers on the top and bottom. When you do have numbers, the plus c is unnecessary. Does that make sense? Okay, great. All right, so the other parts of it, your calculator can evaluate, right? So somebody tell me what happens when you put this first piece inside the brackets before the first plus c. What happens when you put that only into your calculator? What did you get? I saw some of you punching in numbers. Kaylee, did you get one for that part? I saw you guys over here using your calculator. Did you get a value for the first part?
Minus 17.5.
Minus 17.5. And then, of course, there's a fractional form if you like the fractional form better, but this one works just fine. Minus, and then somebody plug in the second part for me, the negative 3, 2 squared over 2 plus 4 times 2, that part. Is it negative? So you have minus a negative like that?
I got positive.
You got a positive? So do you think maybe that it was like this, Christian, with the minus right here? Only? Does that look right? Okay. Yeah, I think that's what I have as well. And then when we combine these, what do we get? Yeah, negative 19.5. And if you want to write it in fractional form instead, that's fine. Decimal's fine here because it's not a repeating decimal or something like that. If we had some repeating decimal or some other form of this, we would want to make sure we looked at it differently. All right. Any questions so far with what this is presented to be? Let me remind you of a couple things. We went through this on Monday, or maybe even last Friday. We can use our calculator in a very helpful way on this, and I'm going to show you 2 ways to use your calculator. Are you ready? Way number 1 is to simply do this evaluation right here without having to key everything in. All right? So I want you to take your calculator, and in the y equals menu, I want you to put in the equation negative 3x squared over 2 plus 4x. So that's going to go in as y1. If you don't have a calculator that has those features, just hold tight for us for a second. We'll get back to the rest of the lesson here in a minute. Okay, so you can put in y1 equals, and you can put in negative 3x squared over 2 plus 4x. Now, you're still going to show me this step right here. The one right there where you actually plugged all the numbers in. You don't need the plus C parts of it, but you're going to show me the rest of that on paper. But in calculating it, you can jump from here down to here using your calculator in one of a couple ways. The nicest way, from what we've done so far, is to use your calculator back in the regular screen to say y1 of 5 minus y1 of 2. Do you remember that notation that we used a couple class periods ago? So remember, you get y1 by hitting vars, y-vars, function y1. You have to put the parentheses. It's the same kind of function notation that we use in an algebra classroom the calculator's using. And then you put the 5. Make sure to close that parenthesis before you do subtraction. This will actually eliminate that middle step, where we actually found out specifically the negative 17.5 and the 2. And it should jump down and give us the negative 19.5. Okay, I see a couple heads nodding. Does anyone's not showing up that way when you did it? Okay, any questions on that method for doing this? I'm about to show you another different method. Are you ready? Okay, we're going to use the same problem because I want you to see that it works. Fantastic. I'm so happy. It's working for you. Great. All right, so you guys ready for another method for doing this? Okay, I'd like for you to take your calculator and I would like you to enter the very first equation that you were actually given. Okay? So this one right here. Negative 3x plus 4 in y1. So we're changing what we're doing. We're going to put this one in y1. So y1 is now going to say negative 3x plus 4. Now, your calculator cannot find for you these versions. The one that Edgar has, I know he's not here today, but the one that he has can do what I'm about to show you without the calculation. But your calculators can figure this out, but it won't actually use calculus to figure it out. It'll use numerical approximations. It'll get the right answer, but it's using some different techniques, okay? So what it doesn't do is it doesn't actually calculate this piece that I just squared in. Okay, it's not going to actually calculate that, and there's not going to be any way for it to sort of spit back out to you that answer, which is part of solving the problem as you're working through it. But what it will do is it will do the calculation using these numbers as the upper and lower limits of integration. So that's kind of cool. All right, so once you've entered the negative 3x plus 4 in your calculator, I want you to exit back to the regular screen. And I want you're going to pull up, let me write down the notation for it. That's not right. Here we go. Yours will say 2, 5. All right, there's two, we've done this sort of thing before. There's 2 operating systems on your calculators. Some of you's operating system looks like this. And some of them will actually look exactly like the problem was with this setup, okay? So here's what I want you to do. I want you to hit Math 9. This is all in Math 9. Okay, so in Math 9, it either says funcint, F-N-C-I-N-T, or F-N-I-N-T. Maybe it doesn't even have the C. Does it have the C? No. No C. I added extra letters. F-N-I-N-T. Or it actually looks like the script S with some blank spots. Okay, so I need to show of hands. Who says FNINT? Okay, about half of you. So let me talk with you about you guys first, and then I'll talk to the others of you that says the other one in a minute. So if yours says FNINT, this is for you. What you're going to do next is you're going to put Y1, so vars, Y vars, function Y1. You're going to put a comma. You're going to put an X, and then another comma. And then these numbers come from the libs of integration. You're going to do a 2 and a 5. And it's not smaller, larger, it's lower, upper. So the lower value in this case is the 2. The upper value, the value on top, is the 5. So you're going to do 2 and then 5. And then you hit enter, and what your calculator does is it's integrating and evaluating all at one time. Does it say negative 19.5? Those of you who have that one? Great. All right, now, who has the script S notation? Raise your hands for me. Okay, Dawn, what does yours have? Does yours have a script S? When you put math 9?
Yeah,
It has the S, or does it have the FNINT?
the F9.
Okay, so yours, you already did yours like ours here? Okay, great. All right, so those of you who have the script S, yours shows up looking something like this. Does that look accurate? Okay, so you need to know what you need to put in each of those places. Well, obviously you know what goes in the first two, right? What goes here and here? That's your 2 and your 5. So you can put in the 2 and the 5 right there. Now, if you didn't already have it there, you could actually type in negative 3x plus 4 here. That would be fine. Wouldn't hurt anything. But if that expression is kind of long and you've already typed it into y1 already, you might just want to hit y1, and you can tell it y1, that equation that I already put in somewhere else. And then this would be x because we have dx at the end of our problem. So yours looks more mathy, right? Less program-like. And then you hit enter. Does it say negative 19.5? Excellent. So both of those are really excellent check steps to make sure that you're making the right kind of progress on the problem. If any of those methods give you different answers, there's an error somewhere. Maybe it's an error in what you put in the calculator, maybe it's an error in something you calculated using the calculus on your paper. It's time for you to go back to check and see which one it is. All right, let's try a different example. You guys can use any of those methods to evaluate. So now it's up to you which ones you like to use. Or you can use just plain old, plug and chug the value straight into your calculator too. That doesn't hurt anything. All right, this one. What do? We start out with? Well, we start out with finding the general antiderivative. So what is the antiderivative of 1 plus sine x? X. Okay, so the antiderivative of 1 is x. And then the derivative of sine is cosine, so the antiderivative is negative cosine. It's the opposite one. And do I need a plus c? No. I don't need plus c if I'm going to be evaluating a definite integral, the numbers on top and bottom. But I do need the line with the pi on top and the 0 on bottom. Does that look okay so far? Okay. Now, again, no matter which method you want to use your calculator to help you with, this next line is going to be on your paper. You're going to write the pi plugged in everywhere. So you're going to write pi minus cosine of pi in parentheses or brackets, and then minus, and then you're going to do the same thing with 0. 0 minus cosine of 0. This one's clean enough, you might just do it in your head. You can certainly use your calculator to plug it in as well. Does anybody remember from trig what the cosine of 0 or the cosine of pi are, what those values are? Cosine, okay, so the pi, at pi it's minus 1. So it looks something like this if you want to enter it by hand. We're going to run into a problem on the calculators. It's going to approximate for us because it's going to have pi in part of your answer, which is going to lead us a little bit it's going to be a little bit less accurate. The second part over here, what is the cosine of 0? Yeah, so this is 1. I know I've got like crazy amounts of parentheses on the problem at the moment. We'll simplify that in a minute. All right, so let's change some of these parentheses. We've got double negatives here and here, which means I actually end up with pi plus 1 or pi plus 2. And your calculator will do a great job of verifying that answer for us now since it's not an exact value, but it doesn't have a way to sort of pull back out the pi plus 2 as the actual answer, when you're looking at it straight on. So double check for me, use one of those techniques we did before, and make sure that we get the same approximation that pi plus 2 gives us. Can you tell me, Christian, what pi plus 2 is in your calculator? Like, what is the approximation we should be looking for?
5.1415.
Okay, so that makes sense, right? Because pi is 3.14. Okay, so as you're doing your calculations with either the function integration or, well, math 9 anyway, or just evaluating out of the y1 of pi minus y1 of 0, do you get 5.1415 dot, 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 more stuff? Does it work out? Excellent. So that's a good confirmation step to make sure that you've got the pieces in there correctly. All right, let's take a look at another example. Oh, first, fundamental theorem of calculus part 2. Told you there was a second part, right? All right, I take it back. Was there a number 3 before that? Did I go too many? I went too many. There we go. Fundamental theorem of calculus part 2. On your test next week, I will ask you to recite one of those two. So you need to memorize the fundamental theorem of calculus part 1 and part 2. You should have both of those memorized, okay? I'll ask you one or the other on your test. So here's the second part. The second part says if f is continuous on the interval ab, and the antiderivative, capital F of x, equals the integral from a to x of f of t dt, then f prime of x, capital F prime of x, equals lowercase f of x. And in terms of, I don't know, visually, kind of what you're seeing happen here, is you're seeing a derivative taken on both sides of this. So if the derivative is taken on the left, you get capital F prime. If the derivative is taken on the right, the derivative notation is sort of canceling out the antiderivative notation. And in doing so, it's taking this x and it's plugging it in where the t is. Can you kind of see those pieces going on there? That might not look very helpful, and I'm going to show you how we actually use that in the problem on the next problem, but this is the second theorem. Okay? Ready to take a look at it? Okay, I'm actually going to do these, well, I guess I'll do them in order. What is different about this function, goes from 0 to sine x of t plus 2, than the notation over here originally? Can you tell what's different about it? I mean, they give us an equation for f of t, that's fine, but there's something that's really different. Going to find a derivative. I just mean the notation of the equation that we're given. Yes. Up here, it doesn't just say x, does it? It says sine of x. If it just said x, it would look exactly like the one before, but now it says sine x, which is something a little bit different. So I'm going to show you how we deal with the fact that that's something a little bit different in this particular problem. And then in the next example, we're going to split something up and do it a little bit differently too. All right, so what this example over here says that I should do is if I want the derivative, I should plug in the value x that's at the top, and the derivative and the antiderivative notation cancel out. That's what that says, right? Okay, so starting out with that description, what I'm going to do here is I'm going to rewrite this. Okay, derivative on the left. I know it looks like a little f instead of a capital F. Just bear with them. It really isn't a big deal what it's called. And I'm supposed to sort of omit the integration notation. And where I have a t, I'm supposed to put in the value that's underlined in pink on top. So it should say now sine of x 2. And of course you'll notice already I put something in parentheses, and you might be saying why. This is where it starts. That's what this over here said to do. It says take the value that's on top and plug it in for x. The difference is that that value is x, and this is sine of x. Okay, everybody good so far? So what do I have to do otherwise? Well, this says I'm supposed to do a derivative, right? But I've got a chain rule in this problem. I don't have just x, I have sine of x. And sine of x has a derivative itself. What's the derivative of sine of x? Cosine of x. So this gets multiplied by cosine of x at the end. So what does it end up looking like? Well, this ends up looking like, we said, it's f of sine x, right? Times the derivative of sine of x. D sine x means derivative of sine of x. So if I don't just have an x on the problem, then I have to take the derivative of what I do have when I'm working through with the answer. And this is done if you really want to distribute the sine through, or the cosine through, and write this as sine x, cosine x, plus 2 cosine x, that's fine. I don't really care. Either one's, really one's not simpler than the other, right? Factored, not factored, it doesn't really matter. Either of those are fine. Okay, so we've got this nuance going on with this function. Now, what's different about this one? Have a 3 minus x, but that could be treated like the sine x, right? Something else. Here's an x on the bottom. Notice this definition over here, what does it have on bottom? A. What's A? A constant. It's a number. X, not a number, right? It's a variable. So what do I have to do? Well, I have to do something a little bit creative, all right? So we talked about a theorem, well, you watched about it. One of the theorems in the last section of the chapter is it says that if I have an interval that went from A to B and there was a C value in between, then if I had an antiderivative that went from A to B, then I can separate it to go from A to C and then C to B. Do you guys remember that? We're going to use that fact right now, right? Okay, so what we're going to do is we're going to take this interval that goes from x to 3 minus x, and we're going to split it into 2 pieces. Because x is a variable, whatever number we want to split it between will work, because it has the ability to go from negative infinity to positive infinity. So we can use any number, and really the number doesn't make any difference anyway. So this can be split. We can go from x to, we might as well go to 0 of t squared plus 4 dt. And then I can go from 0 to 3 minus x. Of t squared plus 4 dt. Okay, is everybody good with that step? We just split it into 2 pieces, and we used the number 0, and there's nothing special about 0 here. No matter what number you pick, it's going to work. Okay? Don't be tempted to actually find any antiderivatives. You are not asked to find an antiderivative on this problem. You are asked to find a derivative, so be careful. I need to do one other thing. This one right here, the second piece, it looks like the last problem, right? I got a number on bottom, I've got something with an x in it on top, but the first one doesn't quite look like that. How is it different?
X is on the bottom.
Yeah, the x is on the bottom instead of on the top, right? You had another theorem in the last section that told you what to do when that was the case. It told you that if you have the integral from a to b, notationally it would say of f of x dx, then you can switch the limits of integration like this if you do what? Do you remember? Make it negative. You can switch them if you put a negative. Is that what you were thinking, Kaylee? Oh, you should have said it. All right. Yeah, you just put a negative in front. So we can take the problem that we're working with and we can change this so it has a negative in front, and then it can go from 0 to x of t squared plus 4 dt plus the integral from 0 to 3 minus x of t squared plus 4 dt. So we have not actually done any calculus truly. Well, I guess we sort of have. We've rewritten using some calculus concept, but we haven't computed anything yet. That's what I mean to say, right? We're supposed to find f prime of x here, yes? And it took us 2 steps before we really had it in the right form to do that. So this one right here is the easiest piece. The first piece, now that it's rewritten, is the easiest piece. It has a negative in front of it. But it looks exactly like this definition, or theorem rather, says it should look. Integral, number on bottom, x on top, function. Which means we can just simply rewrite it and replace the t with x. So this will look like x squared plus 4. Okay? And if you were concerned about this whole thing of, but didn't I just take the derivative of sine x a minute ago? You did. You could take the derivative of x just fine. What's the derivative of x? 1. And it won't change anything, right? So if you want to sort of in your mind to avoid forgetting it later, always take the derivative of what's on top, you could do that. And you'd get a 1 on this one. All right, the next one, again, looks a lot like the one that went from whatever the number was up to sine x. I've got 3 minus x on top, though. So what am I supposed to do? What's the first step? Plug it in, right? I need to plug in the 3 minus x for what? T squared. So I'm going to have 3 minus x squared. And then I'm supposed to have plus 4 because that's the rest of the problem, right? So this, all of this is plugging in the 3 minus x. But what else? Yep, I need the derivative. The derivative of what? The derivative of 3 minus x, right. So what's the derivative of 3 minus x? Minus 1. And as much as you might like to say, I'm done, you're not, right? This one's messy. It's definitely going to get simpler by working some pieces of this out. So let's do that. All right, so this is negative x squared minus 4. That part's clean enough. Take yourself a scratch piece of paper so that we're not spending a lot of space on here, and let's multiply this out. Remember, you can't just sort of distribute the square. That's not okay. You have to FOIL it out. So you're going to do, I'll write mine at the top, 3 minus x times 3 minus x. So if you multiply this out, what do you get? I'll start you out. 9. What's next?
9 minus 6x plus x squared.
Good. 9 minus 6x plus x squared. Is everybody okay with that? Okay, great. So that's going to go next, but that's actually supposed to be plus the number 4, and then I'll multiply everything by a negative when I'm done. So down here, I've got 9 minus 6x plus x squared plus 4, and then I'll multiply those by negative 1. All right, so 9 plus 4, 13 times negative 1, so this is negative 13. I've got negative 6 times negative 1, so positive 6x. It's positive, right? Okay. And then I have positive x squared times negative, so negative x squared. And then I think we have just enough space to write under this and write the combination of everything. So what is the grand sum total that I have here?
Minus 2 x squared minus 17 plus 6x.
Okay, I'm going to put the 6x first just so that it's in order from least to greatest to least. It doesn't really matter. Right? And then you have set minus 17? Sounds good. Any questions on that one? All right. All right, let's do a variation of these now. Find the given area. So the area of the region bounded by x or y minus x. There's no minus there at all, and I've said it twice now. Y equals x squared, and x equals 2, and the x-axis. So they've given us sort of a verbal description of what this image looks like, but they haven't given us any written down integration notation or any of that stuff, so we have to figure that piece out ourselves. Does that make sense to everyone? So the first thing we need to do is we need to graph what we are in fact given so that we can try and figure out what the pieces go together to make. So y equals x squared looks something like this, right? X equals 2. What does that look like? What does x equal 2 look like? You guys know. It's a vertical line, yes. It's a vertical line. So I'll draw my vertical line in something like this. So this was y equals x squared. This is x equals 2. And then your x-axis is the one on bottom, right? So I'll put it in pink just so that we've got it. So I've got this image. And it says I want the area of the region bounded by this, which means I want the part that's sort of triangular in shape that's trapped. You guys following that? So the image that we're looking at is this piece right here. That's what we're going to find. We couldn't do that with geometry because it's really not a triangle, right? If we used a triangle to approximate it, it would be an approximation at best. It would not be exact. So how do I do this? Well, this is exactly what this notation means. It's an integral. And we have to identify what the x value is we start at and the x value is that we end at, moving from left to right. What x value do we begin at? 0. What x value do we end at? 2. And now I need to give the equation that I'm supposed to be underneath. What is the equation that is above where my surface, or my shape rather, is? X squared. And it is stopping at the x-axis, which is exactly the description. So the only thing I have left is dx. So you guys have taken a language statement, you've created a picture for it, and you've used that picture to set up your integral. Does that make sense? Okay, the integration of this is not difficult. What is the integral of x, or the antiderivative of x squared? X cubed divided by 3. We're going to put that vertical line, value 2 on top, value 0 on bottom. You're going to become very friendly with the number 0. Anytime you see it, you're going to kind of smile. Because, more often than not, what happens when you evaluate at 0? It's 0. All right, so the second half of this is 0. What's 2 cubed over 3? It's 8/3. Okay, any questions on that one? All right, there's one other piece of information. And this is the third thing that you would want to have memorized. I think it's highlighted that way on your review sheet. I'll double check. This is called the average value for integrals. And when we get to the example, I'll actually show you visibly what it really is doing for us on a graph. What it says is if f is integrable, that means you can take the antiderivative from a to b, then the average value of f on the interval ab is 1 over b minus a times the integral from a to b of f of x dx. So it looks just like we have been working with before, with what new piece? Yeah, this piece right here at the beginning. And all that is dividing by the width of the interval. So if you take b minus a, you're talking about how wide did you go. Like on this last problem, this would be the number 2, right? It's 2 apart, so we would be dividing by 2 or multiplying by 1/2. So that's the extra piece that we're actually doing this on. So let's do an example, and then I'm going to show you from a graph what it actually does or what it actually means. So this is telling us that we're going to find 1 over 4 to 9 means you do 9 minus 4 times the integral from 4 to 9 of the square root of x. But is there a friendlier way to write square root of x based on what we need to do with it here in a minute? X to the 1/2 is a bit friendlier, right? And then dx. So is everybody good first with the setup? You understand where all the pieces came from? Okay, great. All right, so the 1 over 9 minus 4, that's actually the value what? 1/5, right? Okay. What's the antiderivative of x to the 1/2? Okay, it's 3/2 x to the... No, you're right. So what's wrong with it? 2/3 is correct. We divide by 3/2 or multiply by 2/3. X to what power? 3/2. There's where our 3/2 will go. We don't need a plus c, right? We do need a vertical bar with a 9 and a 4. You can use your calculator to evaluate this, but you can also remember that that over 2 part of the exponent right here is a square root, and 9 and 4 are easy things to take square roots of. So that's actually quite friendly. So I have 1/5. Well, you know what? Let's multiply this. What's 1/5 times 2/3? 2/15. And then I have the square root of 9 cubed minus the square root of 4 cubed. And of course, you don't have to write it that way, but it's helpful because square root is the power that's being over 2. So it's a square root. What's the square root of 9? 3. What's 3 cubed? 27. And you guys can do this in your calculator. You don't have to do this out by hand because it works out nice. What's the square root of 4? What's 2 cubed? 8. 27 minus 8 is? 19 is correct. 19. Yes, we almost 20, right? Yeah, 19. And then if you multiply, this is actually one where you need to have it in fractional form, because if you put it in decimal, it actually is not a terminating decimal. So 19 times 2 would actually be 38. That's correct. Over 15. So the answer to this is 38 over 15. This is the average value. But I want to show you what it means in your calculator. This will take just a second. Take your calculator. I want you to graph y equals square root of x. And I will draw an approximate picture of what your graph looks like. Go ahead and make your graph go from 0 to 9. But we're going to focus, of course, on the graph being between 4 and 9. So the graph looks something like this. And your values should be starting legitimately on the picture that we're looking at from 4 and going out to 9. So roughly speaking, those are the interval we're looking at. And you're finding, obviously part of this says you're finding the area trapped here, right? And in doing that, what this actually does is it takes this area, okay, and you found a value of 38 over 15. I want you to put that in y2. Just put in 38 divided by 15, okay? Now what that's going to do is it's going to give you a vertical line that's going to cut through your graph. It's not vertical, horizontal line is going to cut through your graph, something like this. Okay? What did it do? Well, it basically said that if you took that area, imagine you had Play-Doh or clay or, I don't know, dough even would work. If you took that two-dimensional image and you molded it, my top is not real good, you molded it where it has this sort of uneven top to it, right? It's a curved top, like this, no, like this, I was right. It's this curved top up here, and you somehow were able to mold it to be flat on the top and turn it into a rectangle. That rectangle would have height 38 over 15. That's what it would. The width is still 5, the height is 38 over 15, and you have the same amount of area that you do trapped underneath this curve. That's what average value does, is it finds the average height over that interval by using the area as a reference. So you could actually, and if you calculate, take your calculator and make your window go just from 4 to 9, and it'll be even more obvious that it's really cutting that area to be the same area. So just make your window go from x equals 4 to x equals 9. And do you see it? It should cut through it in such a way that it's balancing the area above that horizontal line and the area below the horizontal line.